The recording. Yeah. Can you see my screen now? Okay.
Yeah,
Yes. So now we are going to start with the first algorithm, that is linear regression. To understand the linear regression, let's understand the case on which we'll be working. So this place you see in the image is a place called Bordeaux in France. And it's very popular for its wines. So this place produces one of the most expensive wine across the globe. Now the problem that we have here is this large difference in price and quality between years. Although wine is produced in a similar way, even though wine is the where technique of making wine is same across the years, still there is a huge fluctuation in the price and quality between the years. Other thing is, it's like you don't sell the wine just after the harvest. You have to keep it in containers for so long. So it's meant to be aged. So hard to tell if wine will be good when it is on the market. So the harvest is, let's say in 2018, it might get sold after 10 years. So now how that wine is going, what price it can fetch after 10 years is very difficult to predict. Okay. And there is a specific profession for this called wine tasters, which predict which ones will be good. Now, our objective here is, can analytics be used to come up with a different system for judging wine? Can analytics be used to come up with a different system for judging wine quality? Okay. Now, predicting the quality of wine. Now, this was done by Mr. Audley Eschenfelder, a Princeton economics professor in the year 1990. And he claimed that he could predict the wine quality without even tasting the wine. Now, if you look into the screen, you can see that he has built a linear model over here with some data. Okay. Now, these two links are the data on which we'll be working. So, we'll be importing it later on. Now, what model this Eschenfelder used? So, Mr. Eschenfelder used a method called linear regression. In linear regression, we predict an outcome variable or a dependent variable. That is my y, with the help of some set of independent variables that are my x1, x2, x3, etc. So in this case, the dependent variable is my wine prices. Since it's difficult to measure the quality of wine, I am like approximating the quality with the prices. So my dependent variable is the price of the wine. So now I have to predict here the price of the wine. And since price is numeric, that's why we are going for a linear regression model. Now after deciding on the price, we have to decide which independent variable should I use to match with price. Means, what are my independent variables on which price can fluctuate? So those can be, one is age. That is because we have always heard that older the wines, the expensive they are. The other conditions could be the weather in which the crop was growing, like AGST, average growing season temperature, harvest rain, winter rain, etc. So now to understand the relationship between my dependent variable and my independent variable, we have created some scatter plots. So on the y we have the price, the logarithm of price, and the x we have age of wines in the first graph. In the second we have price versus AGST. In third we have price versus harvest rain and price versus winter rain. Now you have to answer two questions over here. Number one, the logarithm of price is related most strongly with which variable? I repeat, the logarithm of price is strongly correlated with which of the following four variables? Age of wine, AGST, harvest rain, or winter rain. That's one question. Second question is, why are we using logarithm of price, not price? Think about it. Yes, quickly answer on the chat box. Good, Dhananjay. Good, Pooja. Dhananjay, that correlation answer is wrong. Good, Chaya. Yes, quickly, very few answers I can see. Prince, please answer. Okay, let's see this now. Now let's see the correlation part first. So now you can see that. Okay, how do we measure the correlation between two numeric variables? How do we measure the correlation between two independent variables? Yes, anyone? We have the Pearson correlation or small r. We have small r for measuring the correlation. So this r varies from -1 to +1. So now if you see here, the best relationship you can see here is price versus AGST, which is over here. You can see there's a trend over here that as the price as the AGST increases, the price is also increasing. Right. After that, this you could say we have with age of wine. Again a positive correlation. With harvest trend, you can see it is a negative relationship. As the harvest trend is increasing, the price tends to decrease. And now if you see here, here is almost close to zero. Means price doesn't vary much with winter rain. Okay. So these graphs you should draw for any case. This comes under what is known as EDA. Exploratory data analysis. Means I'm just exploring the data. I'm not building the model as of now. I'm just looking into the various columns I have or various features I have. So now you could say that okay, price and AGST have a very strong correlation. So let's make a model of price versus AGST. Let's start with AGST and then we can use others also. Now the other question is why are we using logarithm not directly price? Now this comes under what is known as feature transformation. Now the price of wine can actually, just a second. Now suppose if my distribution histogram of price is like this. That's my price on the X and that's my frequency. It's a histogram. So now the wine price can go to a really large value also and it starts from a smaller value. So it's actually a very skewed data. The fluctuation in price is too much. Whenever we have such kind of skewness, what we can do is we can always take a feature transformation. Let's say in this case we're taking a log. So what log does is log reduces the scale of this, because we know that if I take log of 10 to the power 6, I will get only 6. 10 to the power 6 is 1 million. Log of 10 to the power 5 is only 5. That is, this is 100,000. So now between 1 million and 100,000 there is a huge gap, but between 6 and 5 just 1 unit. So whenever we have a skewed data, we always tend to take log so that we can reduce the skewness and make it a bit more normal by reducing the scale of it. Is this clear? Now other transformations will be like taking a square root or taking a cube root. Whenever you want to reduce the scale, if you want to increase the scale, for any case you can use x square, x cube, e to the power x, etc. Okay, now let's move ahead. Okay, so now on this Ashton, so when Ashton Filter started to make his model or started to do the study, he got very critical response from all those people who were the wine experts. So Robert Parker was the world's most influential wine expert at that time, and he said that Ashton Filter is an absolute total sham. He's a total fraud. And he compared him to a movie critic who never goes to see the movie but tells how good the movie is just on the basis of the actors and the director. Now let's see this. Yeah. Okay, now answer this question. The plots below show the relationship between two of the independent variables considered by Ashton Filter in the price of wine. So left is price versus AGST, right is price versus harvest rate. Look at these graphs carefully. The question is on the next slide. Now after looking at the graph, answer this quickly. Yes, quickly. Do you want to see the graph again?
Yes, sir.
Here, do this now. Okay, I will show the options now. Yes, Chaya, please answer. Rajesh, Ruchi. Okay, Rajesh has answered. Good Durga, good Pooja, good Abhishek, good Dhananjay, good Pankaj. No, Ruchi, check again. Okay, see this now, let's discuss this. So you can easily see over here that if the AGS, if the temperature is high, the price is also high. If the harvestion is high, the price is towards the lower side. We have a negative correlation, right? So the correct answer is option number C. That is, more harvesting is associated with a lower price and higher temperature is associated with a higher price. So the correct answer is C option here. Any doubts? Yes, any doubts, anyone? Okay, I'll move ahead then. Now let's see one variable linear regression. Now I want to make a model of logarithm of price versus AGST. So now that's my data. So I plotted price versus AGST of all these observations I have. Let's see what is linear regression now. So the linear regression model means that I am going to fit simply a straight line. That is y is equal to some function of x. So if you remember from your high school coordinate geometry that I can write a line in just simply y is equal to mx plus c. Okay. We usually call it y hat because y hat are my predictions. Okay. Y is usually my observed values. Okay. And y hat I will represent rather than this in a similar way but different coefficients beta naught plus beta 1 x. That's my standard equation for linear regression. So y hat is the predicted values, beta naught plus beta naught is the intercept, beta 1 is known as the slope of the line, and x will take my is my independent variable which will take the values of the observations, and that's my predicted value. And now I can also write as y is equal to beta naught plus beta 1 x. So that's my y hat plus error, because actual and observed value won't be same. That's observed, that's predicted. Sorry, observed and predicted values won't be same, so there will always be an error coefficient, error term. Or better way of writing is writing for all the observations that I have on xi plus ei. I hope you will be you're taking notes of all these things. So my yi is simply beta naught plus beta 1 xi plus ei. So that's my observed value, that's my y hat, and that's the error term. So now basically what we are trying to do is, I have this data price versus AGST. Now I want to describe the variation in price with respect to AGST with some function that fits this data. So now I'm trying to fit a line such that this line could be something like this. It fits my data. Means I'm approximating this data set with this line. This is known as your best fit line. Okay. Now if you see here, let's suppose this is the best line that I could make. So once I fix this line means my beta naught and beta 1 are fixed. What is beta naught? Is the intercept. The meaning of intercept is, suppose that's my xy graph, and let's say there's my equation of line. So this value is known as, sorry, not this, from here to origin, this value is known as my intercept, and my slope, that is beta 1, is the inclination of this line from the x-axis. So if I create this line parallel to this inclination, suppose this is theta, then tan theta is my beta 1. So no need to get into the mathematics, just understand that beta 1 is the slope and intercept is this value. So that's your beta naught. So now let's take this point. So for this point, tell me the observed value and the predicted value using this line. For this circular point, can you see my mouse by the way? Somebody says yes, some say no. Okay. What is this? Yeah. For this point over here, this circle, tell me the actual value, observed value, and the predicted value for this point. Very quickly. Yes, Ruchi, answer this. What is my y here and what is my y hat here for this point? Okay, good Dhananjay, good Ruchi. See this now. The actual value is simply, if I see this point in the axis, it will be close to 7.6, 7.7. The predicted value is, for this particular value of x, I'll just put this line over here. Like this point. That's my predicted value. It will be 6.9. That's the y hat for this point, and that's 7.6 to 7.7 is my actual for this point. So to calculate the prediction, what we do, we take this x value and fit in this line. So now all my predictions will be on these lines only, this line, because that's my function here. नहीं समझ में आ रहा तो प्लीज पूछ लेना इसको. This is very fundamental, so you should know these things. So that's my y, that's my y hat, and the difference between the two, that is 7.7 minus 6.9, let's say that is 0.8. That's my error term e. Okay. So if I have 25 observations, I will have 25 y, 25 y hats, and 25 errors also. That's why I'm representing it with the I over here for each and every observation. Beta naught and beta 1 will be fixed, but all these things will change, ei, xi, and yi. Now tell me this, I created the best fit line like this. Okay. Can I clean this? Just a second. Yes, I created one line like this, not like, let's say, this, or maybe like this. Why not? How to decide which line is the best fit?
Wherever the error term is less, right?
Very good. The error term, we need to minimize the error term, right? So first of all, what we have is this has to be minimized to get the line of best fit. Means the beta naught and beta 1 should be calculated on the basis of whichever minimizes this EI. The error of net error for all the observations. Now let's come to the slides. See this now. So that's my equation of regression line I discussed. That's my observed, this is my predicted, and that's the error term. Okay. Beta naught is the intercept coefficient, beta 1 is the regression coefficient. EI is the error term, xi in this case is my temperature, AGST, for the ith observation. And yi is my wine price for the ith observation. So now the best model is chosen in such a way that has the smallest error terms. So the error needs to be minimized. Is this clear?
Himanshu,
Yeah.
one question.
Yes, go ahead.
Yeah, above graph, what will be the beta one?
Sphere
Oh,
for this graph.
yeah.
So suppose now,
Is it the
yeah. So you have to see how when this line intersects the y-axis. So this is
hmm,
actually 15. तो इसको अगर आप बढ़ाओगे तो जहाँ पे ये काटेगा तो ये वैल्यू हो जाएगा.
beta?
This is beta naught. You're asking beta 1, sorry. Beta
Yeah,
1 will be
beta.
the slope of this line. Let's say this angle is theta, then tan theta.
Okay.
If you want to understand slope, suppose this is my line. If I change my x from by 1 unit, if I go from here to here, how much is the change in y? That's known as slope. If I change x by 1, how much y gets changed? That's your slope.
It's
Okay?
related. It's multiplied by the xi, correct? Beta
No, no,
one.
that's just the slope. Xi will be for all these observations. For different observations,
Okay.
it gets multiplied by these values to get the y value. ये देखो.
Okay.
This will be fixed. This keeps on changing and you get different values of y.
Okay. Okay.
Clear?
Okay. Only beta one multiply with the different values of the y. Okay.
X.
X.
Right. So x will be your AGST values. Those 25 values that I have here, इसका 15 है, इसका 15.3 है, this is
Okay. Okay.
15.6 and so on. Okay.
But why we multiply by beta one?
Why we multiply beta 1 means?
Or to the x means it's a multiplication cube of there. Is it formula? You could
No, it's
mention.
like the way of, yes, so the way of writing equation is y is equal to mx plus c.
Okay.
Where m is the slope, x is my uh, independent variable and c is my constant.
Okay. Okay.
Okay. So this m is your beta 1, the slope.
Yeah. Got it. Got it.
Okay. Good. Now, as I told you that we decide the coefficient which has the smallest error terms. Now suppose this is my line of best fit. Okay. Now error term can be written as simply EI, which is yi minus y hat I. Observed minus predicted. That's your error. Okay. Now, to get the line of best fit, what we do is we minimize these errors. So now if you look at this graph, if you can see for all the points above the line, the yi will be more than y hat I, and the error will be positive for all the lines above the line. Sorry, all the points above the line. And for all the points below the line, the error will be negative. So now I have to choose some function to minimize to get the best value of my beta naught and beta 1. If I take the mean of all the EIs, we will always get a 0. We take it as an assumption. The average EI will always be 0, or rather the distribution of EI should be normal. This again second assumption of linear regression. That is my EI should be normally distributed. This means most values should be at the center and few values at the corners. Now what we do is like we minimize what is known as, so first of all we take EI, we take the square of it and then I sum it. For I is equal to 1 to n, that is my all the observations. This is known as SSE, sum of squared errors. And this is that function that we have to minimize to get beta naught and beta 1. We have to minimize this EI square to get beta naught and beta 1. So now if I show you this graph, on the given data I have created 3 lines. One is the red, one is the green, and one is the blue. And these are the SSE values for these 3 lines. So which is the best line over here? The green is the best one. Why? Because it has the least SSE out of the 3. Okay, good. Now before moving ahead, let me tell you one more concept here. Tell me this, when will my EI be 0? All the EIs will be 0. In which case will my EIs be exactly 0? All the EIs will be exactly 0.
When the actual value and predicted value are same.
Very good. When the actual values and the predicted values are exactly same. Say let me give you an example here. Say for example, where is my graph? Yes. Let's say I have this is my data set. Okay, that's my Y and that's my X. This is my observed value, and now I have to create a line of best fit now. Now if I can create a line, okay, which passes through all those points exactly. It should be exact, it should not be one slightly different than them. In those scenarios, you will have all the EIs will be 0. And that's like the best model that you could have. All the points are lying on the line only, means YA and YI hat are equal for all the points. But that's never the case in my real life scenarios, and we have data like this. So now in this case, whatever line you make, you never get EIs as 0. Right? Because no line can pass through all the points. So our objective is to simply minimize the error sum of error square. EI square should be minimized, and that is my SSE. Okay. Now let's understand a theoretical concept here. Let's look at the error again. That is my EI. What is the meaning of error? And what are the what is the root cause for this error? What is the meaning of this error? And why we have this error? Means what could be the contributing factors for this errors?
If there is any unexplained variation, if there is any influence of other variable on the price, like in this case,
Mm-hmm.
then we get error.
Chaya says that there might be some influence of other variables also which you not captured here. That's why you have EI. Good, Chaya. Anything else? Yes, Pooja, that's correct. You can say lurking variables also. Yes, there are some variables which are not in my control. There is one more component. One component you have got it correctly, uh, that it is because of some other. So if you see here, these fluctuation might be not just only because of AGST, but might be because of some other errors also. The other issue here is the quality of model that I make. Sorry, it's going to crash. Just a second. Yes. So the quality of model means if you let me open one more slide here. I hope you guys remember this graph yesterday's one, right? So now in this case, this was the line and this was the curve, and we saw that the curve looks like a better model than the line because curve tries to fit the line in a better way. Okay. Now any error will have two components. One is known as R, other is known as IR. R is the reducible error and IR is the irreducible error. So in this case, it's not like I could make only a linear model. Where is that gone? Sorry. Yeah. In this case, I could have created some kind of a curvilinear model also, right? Something like, let's say like this. And it might be or might not be better than this one. Or I could have made some zigzag models like this also. Okay. So the objective is to get the y correctly predicted, my observed values. Okay. Now try to understand this concept very, very carefully. Let's say f of x is the best possible model that I could make. Means till now we just studied one algorithm, and later on we'll study multiple algorithms as well. And fx is the best possible model I could make, let's say. In this case, it's not like your error will be 0. But in this case, your reducible error will be 0. Means this is the best possible model that you could make out of this data. So you try multiple algorithms, and so it's of course a hypothetical concept because we never know which is the best model. So we keep on making and making and making to reduce the error, but we still don't know how much better I can go. So fx is the best possible model. Theoretical, it's again an hypothetical model that will minimize your reducible error. So what is my linear regression here? Linear regression is my f of hat x. I am trying to estimate my fx. So I say, okay, fine, let's say fx is my linear regression here, which is trying to estimate your fx. Or you could have a polynomial regression also, means some kind of a curvilinear model like this. So all these models that we make in machine learning are all f of hat x. Linear, logistic, decision tree, random forest, all those names you might have heard. They are just trying to find out or give an estimate to the best model that you could make. And that best model will make your reducible error exactly 0. Okay. So in machine learning, all those algorithms are simply attacking my reducible error only. And the best model will shrink it to 0. Other component is the irreducible error, which you guys have correctly identified that in this case I am making a model of price versus AGST. So might be the price might also vary with age or winter rain or harvest rain, which is not captured by this data set that we are using here, and hence we cannot reduce it. We call it IR because it depends on, we need to have more data or more variables or more features to reduce it. And usually we are given with a single data set on which we have to work. More data collection or getting more features is not in our hands. So that's why IR is something that is out of our scope. Means it can only be reduced when we either get more number of observations or maybe more number of features on which my Y can depend. And then only my IR will reduce. So error is always made up of two components, reducible plus irreducible. If you want to reduce the irreducible error, you need to have more data or you need to have more features. Reducible error is the one which you could reduce by making better algorithms, better models. So that's why in machine learning we have so many algorithms. We have neural networks, we have boosting, all those things. They're all attacking the R. IR has to be reduced only with the help of new data. That's why we always say that the data is the king. Because if you have very bad data, the IR will be very high. So whatever model you make, the error component will still be high. But even if you have a good data, means the IR is very low, then a very simple model like linear regression will also give you very good results. So this is the components of your error. Please try to understand this concept. These are like your building blocks of machine learning. So please try to understand this. Okay, Pooja has a doubt.
Can you
again.
please repeat this?
Which part, Prince?
Error. F cap x.
F at x, this one? Okay, I'll repeat.
Yes.
So let me just give me 1 minute, Prince. Okay, Pooja has a question here. What if we are not able to shrink out to 0? Does that happen? Pooja, yes, that will always happen. This is your objective, that I want to make it to 0. Okay. Now the issue here is, I think I have not talked about that. The issue is I am not able to separate these two. Means I don't know how much is R or how much is IR. Because the error that I am measuring is simply yi minus y hat I. That's my error. And it will have R and it will have IR. But you cannot quantify how much is R, how much is IR. If you were able to do that, the machine learning would have been very easy. The reason we are not able to do it because we never know what is the true relationship between y and x. What is the true relationship between y and x? So you never know how much is R and how much is IR. So that's why what you do, you take one data set, so your IR is fixed, and now you keep on building different models. So the total E will be reducing, and you know that okay, if I am reducing E, the R is actually reducing because the data set is same. So shrinking to zero is the best. That's the best algorithm. Will be doing that, but still you won't be able to know if you make it zero. Also, you cannot judge it whether it's zero or not because IR will still be there, and you don't know how much is IR or how much is R.
So how do we decide on how to fix IR basically?
No, you cannot. That's why I'm telling Pooja that see, हमारे पास y रहता है. We have this y that is observed value, right?
Mm-hmm.
Y hat is my predicted from the algorithm. The difference is my error, which has two components. One is R, one is IR, which I am not able to measure separately. So my objective is to minimize this EI as much as I can. So suppose one model can make EI 10, other model can make EI as 5. I will say okay, the 5 one is good. So it will be only be a relative comparison, not an absolute comparison.
Okay.
Okay. So that's why for any data set in a data science project, what you do, you create multiple models on the same data set. So that's why machine learning is a very empirical process, or you can say it's very there's a lot of hit and trial. Because beforehand just looking at data, I cannot say which model is going to work well, and hence I keep on building different models. And whichever is good, I use that. आ रहा है समझ में?
Yes.
Yes, Dhananjay.
Yeah, means in the error R and the IR are the two components.
Yes.
We can't say how much IR is there.
Yes, how much is R, how much is IR, we cannot say.
IR we can't say. So only our part is to minimize the error
Exactly.
by using the different models.
Yes. Clear? Okay. Yes, Prince, I will quickly recap what I talked about. I will try to explain you with a figure over here. Let me see this. Suppose that's your sorry. Let's assume this to be concentric three circles, and let's say this is your dart game. So in the dart game, the objective is to hit at the center, right? So now in our case, the center is my f of x, the best model I could make. It's not y exactly, because y I can never be exactly predict y. So the best will be fx. Now to reach over there, I keep on hitting different time. I can keep on hitting using different algorithms. Say let's say linear regression, which will be here. Let's say decision tree, which is other algorithm which hits here. Let's say random forest, which might hit here. Some other which might hit here also. So now what we are doing, we are trying making different models, and these crosses are my f of hat x. These are estimate of the best model fx. Okay, so out of all this f of hat x, whichever is the closest to fx, that will be my good algorithm, and whichever is far, it will be my not so good algorithm.
Okay.
Getting it? So f of y you can call it like this is my estimate or this is your trials, you can say, of the actual fx.
Mm-hmm.
Clear?
Yes.
Okay. How about others? Any doubt? Abhishek, Balaji, Chaya, Durga, Jitendra?
No question, no doubt.
Okay. So now let's move ahead. So now we were discussing about SSE, that we simply try to minimize my SSE. That is the sum of square errors. And whichever gives me the lowest value, that's my best model. Okay. Now we always use SSE to get the values of beta naught and beta 1 to get the best fit line. But we usually don't report SSE to as an output, that how much is the error in this model. We don't report SSE, we report some other measures. Let's see why. Okay. Now SSE, as you know, is the sum of yi minus y hat I whole square, I belongs to 1 to n. Now let's say I have 10 observations in one case and I have 20 observations in one case. In both the case my line is fixed, that is beta naught plus beta 1 xi. Here also I have same values of beta naught and beta 1. So in both the cases I have the same best fit line. Here I have 10 observations, here I have 20 observations. So in which case your SSE will be higher, the first one or the second one? Think about it, I will just be back in a moment. Yes. What is the answer here? In which case we have higher errors? Okay, I got only two answers. Yes, please, quickly. Yes, second case, very good. In second case, I have 20 observations, and since it is my SSE is yi minus y hat whole square, so I'm basically adding, in this case, I am adding 20 positive terms. Well, in this case, I will be adding 10 positive terms. So my SSE will increase in second case as compared to first case. But ideally, it should be opposite. If I have more observations, I should get a better model, right? So that's the problem with SSE, that it is a function now. It depends on the number of observations also. So SSE will depend upon your n. So rather than using SSE, what we can do, we can simply take SSE and take the mean divided by number of observations. We call it MSE, mean squared error. I'll take measured SSE and I will take the average of it. So we report, so we can, so MSE will be better than our SSE. Now MSE also has one problem. If my unit of my Y is, let's say, dollars, if the Y is measured in dollars, what is the unit of MSE? Or maybe what is the scale of MSE? Yes. Tell me quickly. Or if you're not able to get this, tell me, if Y is in centimeters, what is the unit of MSE? Yes, Dhananjay. क्या वो समझ में नहीं आ रहा क्या?
Hello.
Yes, Dhananjay. If the unit of Y is centimeters, what is the unit of MSE? It cannot be centimeters. What is MSE?
Yeah.
I am taking the square of, right, summation Y minus Y hat whole square. Exactly, it has to be centimeter square. In this case, it has to be dollar square. Right? So now the problem with MSE is, like, suppose my Y is the range of 1 to 10. 1 to 10, let's say. Then dollar square will be, of course, a high value, right? I will be squaring these values. So it might be from, let's say, 10 to 100. So MSE is not very much interpretable. Means, suppose if I say the price of wine vary from, let's say, $30 to $300. Okay. Let's say I took out of this price range, let's say I took a wine of $200. That is my Y. But my Y hat is, let's say my prediction was $150. So it is, the gap is $50 now. That's my error. If I square it, I will get 2,500. So it's a completely different scale than your $100, $200, right? So that's the problem with MSE, that it's not in the same unit as my Y. So how to do that? How to bring dollar square back to dollars? I can simply take a square root. So it's now root of MSE. And we call it RMSE. The same concept we have studied while we studying standard deviation and descriptive statistics. That why we measure standard deviation, not just variance. Because standard deviation has the same unit of Y. Same thing here, we have RMSE. We call it root mean square error. Okay, so we started with SSE, then we moved to MSE, and then we moved to RMSE. But all are the basic function are all of SSE only, that is Y minus Y hat whole square only. Okay. Now suppose I have two models, model 1, model 2. For the first one, RMSE is, let's say, 10. For the second one, RMSE is 20. Which is a better model?
First one.
The first one, RMSE of 10. Why? Because it is a lower value, right? So the lower the value, the better it is. Okay. So RMSE is very good for comparing between two models. That okay, fine, this is a better model than this one. But let's say if I if I tell you like this, let's say RMSE is 10. That's what information I gave to you, that my RMSE is 10. Is it a good model or a bad model? Is it a good model or a bad model? Exactly, we cannot say it. So the reason is RMSE doesn't have any absolute scale. When I say absolute scale means I don't know what is the range of RMSE. Is varying from 0 to 100 or 0 to 10,000 or 0 to 1 lakh. So that's why RMSE can be used for uh, relative comparison between the models, but by just looking at the value of RMSE, I cannot say my model is good or bad. That brings us to the next measure of our error, that is known as R square, and that's the best one. Now R square is what? R square measures it compares the best model to a baseline model. R square compares the best model to a baseline model. Now what is a baseline model? So baseline model means that is the worst model that you can make. You should always remember this, because if you if you say that, if you report to a client, or if you say that okay, my error is so and so, of course he needs to compare it with some benchmark. That benchmark is the baseline model. That's the worst case scenario. Okay. So R square compares your model with the baseline model. Now what is the baseline model in any regression problem? It says the baseline model does not use any variable. Means I'm not going to use AGST or any other variable to do the prediction. Rather, we predict same outcome regardless of the independent variable temperature. सबके लिए I am going to say the same prediction for all the different values of my independent variables. Okay. So in this case, that baseline model is represented by the red. Now my question is, what is this value? How much is this value? Where should I draw this red line? Here or here or here? Where? Yes, anyone?
Sorry, can you please come again?
Yeah. The question is, the baseline model is this represented by this red line, right? So where should be this red line? Means what is just a second. What is this value? Or where should I draw this line? Here or bottom or somewhere here? Okay, let me explain you this. See this now. Suppose you go to a shop. Let's say you want to buy some chocolate. Good, good, Pankaj. Let's say you want to buy some fixed brand, fixed quantity of chocolate. You went to shop A. Okay. He said that the price of chocolate is, let's say, 50 rupees. Shop B told that the price is 40 rupees. Shop C told the price is 65 rupees. Shop D told the price is 45 rupees. Now, after visiting 4 shops, you might have some estimate of the price of the chocolate. What is that? That okay, the price might be somewhere here. What is that value? It's simply the mean of the 4.
Lowest value?
Sorry?
Lowest or
Not the
mean of
lowest, it's usually the mean.
okay, mean of
See, suppose आपको flat, if you want to purchase a flat, let's say, you went to 10 houses nearby, you took the prices of these houses. And the prediction is simply the mean. See this.
okay.
In this case, I have these 11 houses, right? So I can say the average will be somewhere here, some straight line. So I'm not using any feature here. I'm not using the size of house or the brand of chocolate or the quality of chocolate, nothing. I'm just taking the average. So that's the
Without
worst.
any variable that is predicted value.
Yes, exactly. We are not using any X, right? So that's why I'm calling it as a worst case. Means इससे तो better करना ही करना है आपको. Means you cannot be worse than this one. So the baseline model in any regression problem is always y bar. Okay. And now if I have to calculate the error for my baseline model, that error can be written as summation of yi minus y hat के बदले it will be y bar now. Right? In place of y hat, my prediction is simply y bar. This is nothing but SSE only, but we give it a different name, SST. Sum of square total.
So earlier we were calculating the SSC by using the observed minus the predicted.
Right. Here also we are
Now,
measuring the same thing. Here the predicted has become y bar.
Y bar. So
Okay.
it is the baseline.
Yes. Dhananjay, have you seen this formula earlier?
Yeah.
Where?
Yeah. Earlier. Just I came across while reading the articles.
No, just yes. Where? Which part of statistics and what is this formula? किसका है ये formula?
It's like various.
Exactly. It's like the variance of y, right? Not exactly variance. Is the numerator of the variance. Variance of y will be summation of yi minus y bar whole square upon n.
And correct.
Right. So this is actually the total variation in your y. How much your prices are fluctuating from the mean. That's measured from your sum of square total. That's why I'm calling it total, because that's the maximum variation that your price can have.
So, so for in your earlier example of the flats, if your baseline price of the flat is around 35 lakhs, but now if you're looking to new flat which is a go around the 40 lakhs, so the y minus y, so 5 lakhs is the variation.
No, I'm not
5
getting
lakhs
you.
is the
Come
difference.
again, come again.
So suppose in your earlier example, flat example, if you are purchasing a new flat and you have you have reached to the one price that is a 35 lakhs is your baseline price.
Right, that's your y bar
ऊपर और
then.
नीचे मुझे लेना नहीं है, correct? And the new flat price, suppose it's a 40 lakhs. Now you will compare with the 35 and the 40 lakhs.
Right,
So different is the 5 lakhs. So
right. That's for one house. If you have 10 houses, you take for 10 and then you add them.
correct.
Okay, that's will give you your SST. Sum of square total.
Okay.
and that's actually the variance, nothing but the variance of y.
Okay.
Clear?
So in our next models, what we'll use mostly, SSE or SST?
We'll be using R square and RMSE.
R square and RMSE.
Yes, that's the standard way of reporting the errors of any regression problem.
Any regression.
Not only linear regression, any regression problem.
Okay.
Whenever your y is numeric, you will be reporting R square and RMSE. So let's complete this. Let's finish R square quickly. So R square is compares the best model to your baseline model. Okay. So now the denominator is baseline, is it SST? The numerator is your best model. Okay. Now you might have studied this in your regression chapter in lesson in inferential statistics. Summation of yi minus y bar whole square or SST can be broken down into two parts. Summation of yi hat minus y bar whole square plus summation of yi minus yi hat whole square. That's the total variation from your y. Y hat is your prediction and this you are measuring from the y bar. This is known as your explained variation from your model. This I am calling as SSM. But this is not some standard terminology, so don't use it anywhere. SST is more or less standard, SSM is not standard. I'm just calling it sum of square for my model. This is simply the error that we've talked about many times. That's my unexplained variance. And that's my SSE. So your R square is simply SSM upon SST. And SSM can be written as SST minus SSE upon SST. So it becomes 1 minus SSE upon SST. That's your R square formula and that you should remember always. It's 1 minus SSE upon SST and it measures, it has a very good interpretation also. It is the proportion of variance explained of the total variance in y, how much my model can explain. If I can explain more, good. If I cannot explain more, it's bad. R square always lies from 0 to 1. 1 being the best fit, 0 means worst model. Done? Have you written this? Any doubts in R square? Am I not audible?
Now audible.
Okay, I'm not speaking anything. Okay, yeah, I was just giving you, yeah, please write it down.
Himanshu, one doubt about the explain variance and unexplained variance. Can you please explain it?
Okay. Now let's see what is explained and what is unexplained. Let me take the example of this again. Now Dhananjay, you have this price and you have this area of house, right? This
Okay.
is your fluctuation in prices represented by these crosses, right? Now you fit, let's say, this blue model over here. That's your model, right? So now you're trying to capture the variance of your price,
Mm-hmm.
but you are not able to capture 100%. You're only able to capture up to a certain level, right? So that is your explained variance, and whatever is left here, you can call it unexplained. Or
Okay.
let's take the example of wine again. Let me show you this. ऐसे भी समझ सकते हैं आप इसको. बहुत गंदा हो गया ये. Let me clean this. See this now. Let's consider one point, that is this circle. दिख रहा है ये? My mouse might not be visible. See this now. So for this point, that is my yi 8.1,
Mm-hmm.
right? And my y bar is somewhere close to here. Let's say 7. Okay. Now 8.1 to 7. That's your total variation in your y for this point,
Mm-hmm.
right? Now as per this blue line, your prediction will be this,
Mm-hmm.
right? So this value, this one, is your predicted minus y bar. So that's your explained, but still you are able to reach up to here. Means this is still not explained. So that's your unexplained. From the baseline, I could go up to here because of this blue line, because of this AGST model. So this much out of the total variance from here to here, I could explain this much, but still this is again remaining. So that's my unexplained variance.
Okay. Okay. Okay.
Okay.
Sounds good. Okay.
Well, let's quickly move here. Now it's already 8:27. Yes. Any doubt in what is R square? Anyone? So for now, what is this question here? Yes, Pooja. Pooja has a question here. Does within group and between group variability also comes into picture? Pooja, you can call this, the first bracket is your between group variability and the second bracket is your within group variability. So if you want to, is in terms of NO, if you are talking, this is known as between group, this is known as within group. Okay. Now I have SSC and SST. So my R square can be simply calculated as 1 minus 5.73 upon 10.15. Can somebody please quickly calculate this? One minus 5.73 over 10.15. That's 0.435 or 0.44. That's my R square value. So now the best could be 1. So we are still halfway around. So this is not a very good model. Okay. Now let's quickly do this. Interpreting R square. It says R square captures value added from using a model. R square is equal to 0 means when will be R square 0? When SSC and SST are same. So this will be 1 and this will be 0. R square means 0 means no improvement from the baseline model. It's just y bar only. R square is equal to 1 means a perfect predictive model. R square 1 means SSE is 0 and means y and y hat are all same. R square 1 is means a perfect model. 0 is a bad model. Right? In real life scenarios, you never get exact 0 or exact 1. You get something in between only. So we usually 0.7, 0.8 is considered a good model. 0.1, 0.2 is not considered a good model. The benefit of R square is it is unitless and universally interpretable. It is unitless and universally interpretable. Okay. But it also has some issues, of course, which we cannot resolve them, but let me tell you that. One issue is it can still be hard to compare between two different problems. If on a same data set, if I have R square as 0.4 and R square as 0.6, I can blindly say yes, the 0.6 is a good model. But if I have completely two different problems, let's say one is data set 1 and one is data set 2. Let's say two different problems. It says good models for easy problems will have R square close to 1. Good models for easy problem will have R square is equal close to 1. But good models for hard problems will still have R square close to 0. I want you to explain me these 2 points. And hint is, think about R plus IR concept, reducible plus irreducible error, which we studied earlier. Yes, quickly. Just one announcement. The next slide is a quick question which I want you to do as a homework. Tomorrow's class will be starting with discussing this homework. Just this question, one question, which is on this next slide. Okay. This is your homework for today, and of course the revision of the today's video. I'll share the videos within the next 2 to 3 hours. Otherwise, you anyways have it on Moodle also. Answer this now. Yes, Pooja, you can take that. Yes, Dhananjay, you are correct. Good. Okay, let me take some names here. Yes, Balaji, I want you to answer this. Balaji, question is, these are the 2 points. Good model for easy problem will have R square close to 1. Well, good model for hard problems will still have R square close to 0. Explain these 2 points quickly.
Yes. Like when we say good models for easy problem will have R square is equal to 1 means the base, when we compare with the base model,
Mm-hmm.
our model is very good. It is not like base model lies very low, and our model gives a good results. That is why R square is approximately equal to 1.
Fine. Now the last point.
Whereas like
Mm-hmm.
good models for hard problems still have, means it is like nothing but our models lies almost equal to the base model, where we consider as base model as worst model. So we cannot take that model as a good model for our problem.
No, but it says good model. It says good models for hard problems still have R square close to 0. If you're saying that it's not a good model, then why is writing it good model? Balaji, think on the lines of reducible and irreducible error. Yes, Abhishek
Okay,
Kumar.
might be irreversible error, like data is very less, or like
Mm-hmm.
features wise it is very less, so it might lead to R square is approximately.
Okay, let me explain this. Okay, fine. Balaji, you're very close. See this. For hard problems means, suppose I have a very complicated data set, means I know that I have my y depends on, let's say, 50 variables. I know my business problem. But due to some reasons, I'm not able to collect the data for 50 variables. I could collect the data of only 5 variables. And now I'm building a model on this 5 variables only. So how good model I make, still I can get only up to, let's say, R square of 0.2. I cannot be better than this. The reason is my irreducible error is very high in this case. Because it's a complicated problem, I cannot capture all the variance. So my irreducible is very high. So a very good model will also not take you very much further. Means the take home lesson is, if my R square value is 0.2, that doesn't guarantee that your model is bad. The scenario might be that the data is also very bad. So just be careful. Okay. For easy problems, where we have, let's say, so my y depends on, let's say, 2 or 3 variables, and I have all the data. In those scenarios, even a very simple model can get you R square close to 1. So of course that's a good model. But in the third case, this third statement, R square of 0.2 is also a very good model. But since the data is bad, you cannot go beyond this 0.2 value. Clear?
Yes.
So in this case, my IR is high. That's why I could not go to 0.7 or 0.8. I'm still close to 0.1, 0.2 only. Okay, fair enough. Thank you so much. Any other doubts in this? Okay,
No.
those who want to leave, they can leave. Others can, if they have any doubts, they can stay. The class is over. Tomorrow we'll start with the next topic. Just do this next question as a homework. Yeah, thanks Jitendra, thanks Pooja, thanks Ruchi,
Yeah.
thanks Chaya. Yes.
Himanshu, will you be sending the question, like emailing us or something?
Which one? This no, it's already in Moodle. Machine learning is open for you.
Okay, okay,
Just go to Moodle,
okay,
you'll find the machine learning section. You'll find the linear regression topic, wine case study, and within that you'll have the slides.
okay,
If you
okay.
don't find,
Thank you.
just ping on the group. Venu will do that for you.
Okay,
Okay. Yeah. Thank you.
thank you.
So please revise it. It's not an easy topic. Do revise it.
Himanshu, this is Praveen here.
Yes, Praveen.
Himanshu, regarding that R videos, right? How could I get access to that model, Himanshu?
Of the previous batch?
No,
Sorry,
this
this batch
current.
only.
Uh,
Have you talked? Have you talked to him, Kush?
yeah, I mailed to Kush.
Okay, I'll just give me today's time. I'll just ask him.
Okay,
Just
thanks.
give me 1 or 2 hours. You know?
Okay, Himanshu. Thank you.
Okay, thank you. Yes, okay, I'm closing it now. Thank you.